Good morning, good afternoon, and good evening, everyone. We still have our participants logging in, but we have a fair amount of number now. So I will go ahead and start with the introduction and welcoming everyone to the seminar. My name is Eugene Choi. I'm a junior policy analyst within Test Guideline program at the Environment, Health and Safety Division at the Environment Directorate of the OECD. I'll be narrating the webinar today. The webinar today focuses on presentation on the implementation of first standalone NAMs for eye hazard identification into OECD guidelines. So now the two guidelines referenced here are published. This is OECD Guideline 467 and Test Guideline 492B. They're both available in the public domain on our website. Without further ado, I'd like to introduce the three speakers for today's webinar. First, we have Dr. Joel Garrison, who is a scientific officer at the European Commission Joint Research Center. Then we have Dr. Els Adrians, who is a consultant and also CEO of Adrian Consulting, collaborating with many industries and regulatory tasks for different endpoints, including the irritation. And finally, we have Dr. Natalie Alepe, who is a scientific officer at the L'Oréal. So welcome panels, and thank you for providing your presentation today. So the webinar program will be as following. We first have a presentation on the Draize eye test reference database, and then on the OECD Test Guideline 467, going into the defined approaches for serious eye damage and eye irritation. And then the third part will be on the OECD Test Guideline 492B, another test guideline that was approved this year for classifying 3 eye hazard categories. Just a few logistics to go over. So for the Q&A, we would like to ask the participants to enter your questions directly to the Q&A chat box. So you should be able to see the little icon shown here on your Zoom platform. You can enter your questions anytime during the webinar, and you may indicate the speaker to direct the question at this time. Some questions may be answered in the chat box directly, and some questions will be discussed during the Q&A sessions that is reserved at the end of the webinar. Okay, so without further ado, I'd like to invite the first speaker for this webinar, Dr. Joel Garrison. Joel, please go ahead.
Hello, everyone. Thank you, Eugene, for the kind introduction, and thank you for inviting me to present here today. Let me share my slides. I hope you can see them now. Well, and thank you all participants for being here with us today. I hope you will enjoy this webinar. So I was asked to talk about the Draize eye test reference database. And I will start this talk by giving a bit of an historic overview in the area of serious eye damage and eye irritation. So there were several major international validation efforts in the 90s where methods were validated as full replacements to the Draize rabbit eye test. However, these studies were mostly unsuccessful. And it was concluded back then that no single in vitro method was capable of replacing the Draize rabbit eye test. It was recognized that most in vitro tests only partially model in vivo responses, and that therefore it would be difficult to replace the Draize rabbit eye test with one single in vitro method in the foreseeable future. But it was also agreed already back then that animal data were of limited quality and low reproducibility, and that this affected the evaluation of the validity of the in vitro methods. In 2005, ECVAM at the JRC organized an expert workshop where a conceptual framework of a testing strategy for irritation was developed. Basically, depending on the physicochemical properties and anticipated degree of irritation of a chemical, a so-called top-down or bottom-up approach would be initiated. So methods with high specificity for the identification of serious eye damage or ocular corrosion should be used to initiate the top-down approach, while methods with a high sensitivity for the identification of no classification should be used to initiate the bottom-up approach. This bottom-up and top-down strategy then served as a basis for many validation studies in the following years, where methods were assessed for identifying either serious eye damage or no classification. And these efforts led to the acceptance of several partial replacement NEMs as OECD test guidelines. They could be used standalone, but only to identify parts of the irritancy scale, mainly no irritation or serious eye damage or category 1. Still, 7 years after the ECVAM workshop, there were still no methods accepted internationally for identifying no classification or non-irritants. So in 2013, the test guidelines on BCOP eyes and isolated chicken eye were finally updated to allow the identification of non-irritants, but false negative results were not acceptable by regulatory authorities. So for example, the original prediction model of the isolated chicken eye had to be revised during the acceptance process to reduce the rate of false negatives at the expense of false positives. So in collaboration with Cosmetics Europe, we at the JRC started to work on the variability of the Draize eye test. And in 2014, we published a paper proposing the concept of drivers of classification and acceptance levels for false negatives based on the Draize variability. In 2017, we published a second paper with the Draize eye test reference database to support the selection of chemicals for the development and validation of NEMs. I will focus my presentation on these two papers from 2014 and 2017. Also in 2017, the OECD published an IATA for serious eye damage and eye irritation, where the concept of the top-down and bottom-up strategy was integrated. Last year, we had a major breakthrough in this area with the introduction of classification criteria based on EMS in GHS chapter 3.3. The revised chapter will be published next year in revision 10 of GHS, but it can already be accessed through the links I've included on this slide. And I suppose the slides will be made available to all participants afterwards. And this year, after more than 30 years of investment in this area, we have finally hit the jackpot with the publication of the OECD, by the OECD of the first test guidelines on NEMs that are able to fully replace the Draize eye test, namely two defined approaches and the kinetic HC time to toxicity. These are the main focus of today's webinar and will be described in detail by the next two speakers. So even though the revision of chapter 3.3 of GHS was concluded last year, before the adoption of these test guidelines, the concept of defined approaches is already integrated in the chapter, and kinetic HC time to toxicity is also mentioned there. So, as I mentioned, my presentation will focus on the work published by Cosmetics Europe and the JRC in these two manuscripts. And I truly believe this work provided a turning point in the area of serious eye damage irritation and paved the way to achieving full replacement of the in vivo Draize eye test, which 10 years ago actually looked pretty daunting and almost impossible to achieve. In fact, until last year, only partial replacement with NEMs had been achieved. We had several methods to identify no classification and several to identify serious eye damage, according to the bottom-up approach. But the identification, the identification of eye irritation remained difficult, if not impossible. mostly due to the high rates of false positives of the methods accepted for identifying no classification, but also the false negatives of the methods accepted for identifying serious eye damage. So to better understand the reasons for this failure, after more than 20 years of investment in the area, Cosmetics Europe and the JRC decided back in the early 2010s to perform a systematic analysis of historical in vivo rabbit eye data in view of identifying the most important in vivo endpoints driving GHS classification and evaluating the Draize eye test variability. So with this work, we wanted to identify possible gaps in the available NEM battery and understand their limitations, and also propose acceptable performance benchmarks for NEMs, in particular, acceptable levels of false negative rates, which would depart from the notion at that time that NEMs should produce no false negatives at all. So I would ask the question, what it means that a certain NEM has, for example, 80% accuracy against animal data. Does it mean it fails 20% of the time? Or does it mean that the uncertainty in the reference data is such that you can actually never reach 100% accuracy? So these were the types of questions we wanted to answer with this work. So how does the Draize eye test work as described in OECD Test Guideline 405? So according to the UN GHS classification, there are 4 endpoints that are analyzed in the Draize eye test. So corneal opacity, iris lesions, conjunctival redness, and conjunctival chemosis. And these are scored according to the scores you see here. So these tissues are observed for up to 21 days, and you annotate the scores. And the scores from days 1 to 3 are averaged. A mean is calculated for each rabbit for those 4 endpoints. And these are then used to decide on classification based on thresholds for those means. Apart from this, one also looks at corneal opacity score 4, which is the highest you can have. And if it appears in any animal or at any time point, you would also classify a chemical as category 1. And on top of this, we also look at the persistence of effects until day 21. So if any of these 4 endpoints shows scores above 0 on day 21 in any animal, that could lead to a category 1 classification. Then persistence on day 7 is used to decide between category 2A and category 2B, but I'll come back to that in the following slide. So we named these different criteria as drivers of classification. GHS has 11 drivers of classification in total, and we describe them in this first publication of 2014. So for category 1, they are corneal opacity mean equal or above 3, and iritis mean higher than 1.5, for immediate severity appearing during the first 3 observation days in at least 60% of the animals. Then persistence of any effect on day 21 in at least 1 animal can also drive classification, a category 1 classification, as I mentioned, and a corneal opacity equal to 4 in any rabbit at any time point in the observation period can also lead to a category 1 classification. So for category 2, these drivers are corneal opacity mean equal or higher than 1, conjunctival redness mean equal or higher than 2, conjunctival chemosis mean equal or higher than 2, and iritis mean equal or higher than 1 for effects appearing during the first 3 observation days, again, in at least 60% of the animals. And as I mentioned, depending on the reversibility of these effects on day 7, chemicals may be further divided into categories 2A and 2B. So chemicals are not classified if none of these 11 drivers described for category 1 and for category 2 are fulfilled. And I guess until we did this work, no one actually ever looked at what was actually driving the classification. You just decide on the classification based on an analysis, a global analysis of all these drivers. But no one actually understood the importance of each one of them for classification. So our work focused on two main databases, namely the European New Chemicals Database, which contained all chemicals introduced in the EU industrial market between 1981 and the entry into force of the REACH legislation, and the Draize Sce Test Reference Database, or the RD, which pulled together all chemical lists that had been created to support validation studies. Only studies with complete animal data were included in the DRD, since the New Chemicals Database only provided summary data. It was not included in the DRD. So the DRD only included studies for which we had full animal data, and we could actually curate completely the database. You can see that the prevalence in the two databases looks different, which is expected because the DRD, being a database that was put together to support validation studies, was enriched in classified chemicals. If you look at the prevalence in the New Chemicals Database, which is probably much more closer to the real world prevalence, you see that the prevalence of Cat1 chemicals is quite low, and Cat2 as well. So it accounts for less than 20% of the chemicals. And the great majority is not classified. So obviously the need here, the most pressing need was for methods to identify no classification. And that's where we had most difficulties because of the requirements for very low false negatives from regulatory authorities. So we then compiled, when we compiled the Draize Sce Test Reference Database, the idea was really to provide a list where all chemicals were categorized according to their GHS classification and the main effect driving the classification, because this could really help people understanding limitations in their methods, selecting a proper list of materials for validation studies that would cover all the main drivers, and also understand which drivers were less important and therefore not so important to cover in vitro. We also looked at multiple studies for the same chemical and tried to inform the community on which chemicals should not be included in validation studies due to high uncertainty. The main driver for each chemical was identified as the one having the highest number of animals fulfilling the classification criterion. For instance, for category 2 chemicals, between corneal opacity, iritis, conjunctival redness, if all of those had more than 60% of chemicals fulfilling the classification criteria, the main one would be the one with the highest number of animals fulfilling that criteria. And you can see a glimpse of the database where you see the chemicals grouped according first to severity, then chemicals that had persistent effects but without severity in the first 3 days. So they were classified just based on persistence. And then based on other types of observations like corneal opacity equal to 4, where severity was not enough to drive classification, and many times persistence was unknown because the study was stopped before day 21. And the same for category 2 chemicals, where you see the main driver and you also see whether persistence at day 7 is existing or not, and therefore the chemical would be classified as 2A or as 2B. So okay, I'm having some problems with my computer. Sorry, my computer just blocked.
Joel, would you like me to share the screen?
No, it's okay. I'll just share it again. It's okay. It's just, yeah, just crashed PowerPoint. But if you give me just, I'm opening it and I'll. So I was here. Let me.
I need to take this opportunity to again encourage the participants to enter their question in the Q&A session.
So can you see it now again?
Yes, yes. Very good. Thank you.
Okay, sorry for this, but here we go again. So so basically the DRD contains 681 independent in vivo studies on 634 individual chemicals. So you can see there are a few repeated studies that we could actually analyze. It contains a description of all the ocular effects observed in each in vivo study. As I said, the categorization is according to the main driver of classification, and it contains in total 165 category 1 chemicals, 79 category 2, 342 no category or not classified, and there is also 94 studies where the study criteria were not met, which are not recommended for inclusion in validation studies, but for completeness were also included in the database. An analysis of the in vivo drivers of category 1 classification in the new chemicals database show that about 28% of the Cat 1 chemicals are classified based on severity of effects appearing on days 1 to 3. And most of these classifications are based on corneal opacity. A much larger proportion of the Cat 1 chemicals, about 65%, is classified based on persistence of effects without severity in the first 3 observation days. And again, corneal opacity is the main endpoint driving classification. So this means that NEMs should be able to identify persistent effects. Iritis, on the other hand, rarely drives classification on its own. It's for less than 4% of the chemicals. So there is no need really to address this endpoint in vitro. So looking at the distribution of in vivo drivers of classification in the DRD, one can see a similar pattern. And you can see already that the corneal opacity is usually the endpoint that is most prevalent for category 1 chemicals. So on the right-hand panel, you see the total amount of drivers. So every single time a corneal opacity appears, or corneal persistence or conjunctival persistence and so on. On the left-hand panel, you see the main driver. So the one we consider the main driver based on the number of animals. And if you look at this, you can see that corneal, for category 1 chemicals, the corneal opacity is much more important than iritis. And some of these chemicals with iritis also show corneal opacity. It just so happened that for some, there were more animals with an iritis score above cutoff than for corneal opacity, but corneal opacity would still be involved there. And you can see also that corneal opacity persistence is much more important than conjunctival persistence. Now, what I wanted to say also is that a lot of the persistent effects, for instance, for corneal persistence on day 21, a lot of them occur in a minority of the animals. So while for severity in days 1 to 3, you need to see effects on the majority of the animals, for persistence, it's enough to have one single animal showing an effect to derive a classification. And you can see that 47% of these chemicals classified based on persistence only show the effects in a minority of the animals, so less than 60%, many times in a single animal. The same for conjunctival persistence, so 30%, 33% occurred in a minority of the animals. And actually 33% that had effects in the majority of the animals, but showed conjunctival scores of 1 on day 21. And I remind you that the classification cutoff for category 2 is more than 2. So this means it's a score that is actually not even considered for category 2 classification. But unfortunately, when it comes to persistence, full reversibility is considered 0. I would say here that, for instance, in the US EPA, a score of 1 for conjunctival effects is considered fully reversed on day 21, but not in GHS. And for CO equal to 4, also 44% in the minority of the animals. And also even within the CO and conjunctival persistent groups, 5 studies even showed no irritation based on scores of days 1 to 3, which indicates that there is some sort of delayed effects that are driving the classification. And I'll come back to this now on this slide. So what we then did was to look at the distribution of individual corneal opacity grades for the category 1 chemicals classified based on persistence in the majority of the animals against those classified cat 1 based on persistence in the minority of the animals in the middle panel, and on the right hand, the category 2A chemicals. And what you can see is that actually there is a very similar distribution of CO grades in these 2 panels. There is no way one can distinguish one group from the other based on the scores on days 1 to 3. And in fact, category 2A chemicals even show higher medians in the first 3 observation days than those classified based on persistence in a minority of the animals. You can also see that in this middle panel for persistence, there are several delayed effects appearing, which actually quite often would drive a classification. And these delayed effects could many times be due to other things than the chemical itself. For instance, animal behavior, secondary infection, and other types of effects that are actually not chemical related, but we are classifying these. And obviously, these are things that would be very difficult to predict in vitro because they are really not derived from chemical action. We did a similar analysis for conjunctival redness, and the conclusions are quite similar, that the distribution of grades is quite similar, if not identical, in the first 3 days. The medians in this case are also similar, but in this case, even similar to those for the category 1 based on persistence in the majority of the animals, so in the left-hand panel. And this actually questions the utility of conjunctival effects to classify chemicals as category 1. So an analysis of the in vivo drivers for category 2 classification in the new chemicals database show that about 54% of the category 2 chemicals are classified based on corneal opacity, but only 20% do not show classifiable conjunctival effects. A much larger proportion of the category 2 chemicals, about 75%, is classified based on conjunctival redness, and about 40% do not have enough corneal opacity involvement. So this means that NAMs should be able to identify at least conjunctival redness. And finally, conjunctival chemosis and again iritis rarely drive classification on their own, and we're talking about less than 5% in total. So there is really no need to address conjunctival chemosis or iritis in vitro. So as I said in the beginning, we also did an analysis of the variability of the Draize eye test in order to identify acceptable performance benchmarks for the evaluation of NAMs. And we looked in the first paper in 2014 at the within test variability on classification. And we could notice that the over classification error for not classified and category 2 is negligible, less than 1%. However, due to the variability of individual NO responses within the same test in the in vivo Draize eye test, there is an overall probability of about 12% that chemicals classified as GHS Cat2 by the in vivo test could be equally identified as not classified in a repeat test. And the same for category 1 chemicals, where at least 11% could be equally identified as CAT2 in a repeat test. And this obviously only counting within test variability. Here we were not even addressing between test variability. That analysis we did in 2017 when we published the RD, and we could observe that chemicals with at least one category 1 study show only 63% concordance, while for category 2 there was 71% concordance. And if we would consider 2A and 2B the concordance decreases to 43%. And more recent studies or studies published more or less about the same time, looking at the ECHA registration database, showed similar results and quite a low reproducibility of the Draize eye test. So I would say that it is quite important to consider the uncertainty of the reference data when defining acceptance levels for false negatives and false positives for the development, validation, and regulatory acceptance of NAMs. Based on this analysis that we did already in 2014, when we actually validated the ECVAM, validated the reconstructed human corneal epithelium models, epiocular and skinetic, already the validation management group agreed that 10% false negatives would be definitely acceptable. And we only consider that it would be definitely unacceptable to have more than 20% false negatives. And this was actually the first validation study that already upfront agreed to a certain level of false negatives. And this guideline, when it was submitted to the OECD, took about a year to get acceptance. So it was actually quite fast. And it was the first time we had a certain number of false negatives accepted at OECD for irritation. So in conclusion, the DRD is a curated database of in vivo Draize eye test data. And it's an excellent and very valuable tool to support validation studies. The analysis of drivers of classification identified the most important endpoints to address in vitro and helped identify gaps and limitations. The analysis of the variability of the historical animal data was used to inform performance benchmarks for NAMs. And I would stress that the high uncertainty of the animal data is indeed reduced in the DRD, but it's not removed. I mean, I would say that for most studies or most chemicals where we had more than one study, we ended up having to recommend that chemical not to be used in validation studies because the studies were just not reproducible. So we weren't certain of which classification would be the correct one. But for the majority of the studies in the DRD, we have a single study. Where classifications were based on the minority of the animals, where we saw delayed effects, and we did all these analyses, we recommended those chemicals not to be used to increase a bit certainty of the animal data. But still, there is a high uncertainty still. The data are still variable, and I think that needs to be kept in mind when analyzing NAMs, even when the DRD is used for chemical selection. And just, I would like to leave some final thoughts on this last point. So in recent years, quite some attention has been given to the assessment of the quality of reference animal data. And it is quite clear that the variability is so high and the quality so low that it becomes almost meaningless to use these as reference to judge the performance of alternative approaches. Moreover, most animal models lack human relevance. Yet, there is still a too high focus on gold standards and predictive capacity when judging the scientific validity of non-animal methods for use in a regulatory context. And I still see this, even in the area of irritation, where it is clear that the traditional animal test lacks validity. We should therefore focus on developing approaches that protect human health or the environment, rather than trying to be predictive of animal data. And in order to do this, we need to depart from purely data-driven demonstration of relevance and bring more focus to biological relevance and mechanistic understanding. Where comparisons between animal and NAM data are still made, it is important to acknowledge the uncertainty of the reference in vivo data, when establishing acceptance levels of false negatives for NAMs. And I would just, this is the last slide, would just like to bring your attention to two recent papers that I co-authored with colleagues in NICETM, US agencies, EPA, and others, and also colleagues from the PITA Science Consortium International, which actually focus a lot on what I've just said in the last slides. The first one is about evaluating methods for eye irritation based on human biology. And the second one is proposing a framework for establishing scientific confidence in new approach methodologies that tries to depart from pure focus on predictive capacity. And I would highly recommend you reading these two papers if you're interested. Well, with this I finish, and I thank you very much for your attention.
Thank you very much, Joel, for this presentation. I will now ask Joel to stop sharing and then invite the next speakers, Els Adrians, to share her presentation. The work described in Joel's presentation provided a strong foundation that helped the development of this PA and the test method that we presented. It also exemplifies how the existing data can be used to gain more insights for improving the current practices, and also motivating further the efforts to develop a NAMS approach. Okay, now I invite Els to the floor. Please go ahead, Els.
Thank you, Jen, for inviting me today to give the talk. On the second presentation, which is on the defined approaches for serious eye damage and eye irritation. It is TG467. But first, I would like to go back to the slide of Joel and start with, yeah, I thought that the animation was not working properly. And start with, yeah, the jackpot. One of the jackpot methods of 2022. So, as already mentioned by Joel, there are several single OECD adoptive test methods available for the identification of UNJHS category 1 and for no category. But the problem was category 2. Now, by combining several OECD adopted in vitro test methods with or without physicochemical properties, we were able to identify the three UNJHS categories for eye hazard identification, which is now included in OECD TG467. And the inclusion of the methods is based on the IATA, so the integrated approach to testing and assessment. And I will explain a little bit further during the presentation with some illustration, the top-down and the bottom-up approach that can be used with the defined approaches. But first, I will explain a little bit more on the applicability domain. So DAL1, which stands for Defined Approach for Liquids number 1. This one is applicable to neat non-surfactant liquids and is based on a combination of two OECD adapted methods and physicochemical properties. And the second defined approach, DL2, is applicable to non-surfactant liquids, liquids and solids dissolved in water. And this one is based on two OECD adopted in vitro test methods. I will go into detail on the data interpretation procedure or the DIP. And I will show the performances of the DL1 and DL2. And finally, I will also illustrate the data interpretation procedure with 4 chemicals. But first, I will explain why we the DA is restricted to non-surfactant liquids. Therefore, we have to go back to 2018 or even earlier. During the Conjunctival project, a set of 80 reference chemicals that were selected from the DRD that was explained by Joel. It were liquids and solids, and they were tested with 8 different in vitro test methods. And then later on, the set of chemicals was enlarged to 145 substances. And the substances were liquids, solids, and also surfactants. The first analysis showed that the predictivity was better for liquids as compared to solids. So this is why we restricted the DA to liquids only. And then furthermore, the surfactants were also, or not applicable into this DA because the underprediction rate for in vivo CAT1 for surfactants was too high. Then, as I mentioned already, the source of our Draize data, or the reference data for the liquids, was a Draize reference database, or the DRD. And the important drivers of classification were represented in our data set. So it is CO severity or corneal opacity severity, persistence of corneal opacity for category 1. So actually the groups with the drivers with the gray background were represented in our study. And then for category 2, it is corneal opacity and conjunctival effects. So there were no specific liquids that were classified based on irities only in our data set. And then for the subgroup of the chemicals that do not require classification, we have liquids with some that induced some corneal opacity, but not enough to result in a classification. And then also liquids that did nothing at all. So they had no effect on the corneal opacity. So they are this group is called CO equals 0. Then the chemical space. So we had a broad range of chemical classes, different industrial uses, and 79 different organic functional groups were represented in the set of liquids. And here you see the list of OFGs that were most common. So it means that more than 10 liquids were represented for each of those OFGs. We will first focus on the components of the L1. So we use physicochemical exclusion rules to identify no-cut. And they are based on the following properties of the neat liquid. So it can be based on water solubility or on a combination of 3 properties, which are octanol water partition coefficient, vapor pressure, and surface tension, but surface tension of the neat liquid. The second component is the reconstructed human cornea-like epithelial models, or the RHCE models from OECD TG 492. And they are used to identify no-cut. And we evaluated 2 methods, epiocular, which is called validation reference method 1, as in the guideline, and then skinetic human corneal epithelium method, which is called VRM 2, according to the, as in the guideline. So both methods, the evaluation of the eye hazard potential of a test chemical is based on its ability to induce cytotoxicity in the RHCE tissue construct. And then the third component in the DL1 is the bovine corneal opacity and permeability test method. where we use the laser light-based opacitometer, or the LLBO, according to OECD TG437, and we use it to identify category 1. And the eye hazard potential of a test chemical is measured by its ability to induce opacity and increased permeability in an isolated bovine cornea. But we focus only on the use of the opacity in our defined approach. Here you can see the data interpretation procedure of DL1 in a bottom-up approach. So we can start with the physical chemical properties. So if the water solubility is very low, less than 0.02 milligram per ml, then the chemical is predicted no cut. Or if the combination of the three properties, so log P and vapor pressure are above 1 and above 3, or the surface tension of the neat liquid is below 30, then the chemical is predicted no cut. If this is not the case, then we continue with the OECD TG492, where you can use the epiocular or the kinetic test method. And if the cell viability is less than more than 60%, you have you can predict the liquid no cut. If it's less than 60%, then you continue with the OECD TG437, the BCOP LLBO. And if the opacity is bigger than 145, then the chemical is predicted category 1. If it is less than 145, then the liquid is predicted category 2. But you can also use a different variation of the dip. So start with an RH-CE, followed with the physical chemical properties and the BCOP LLBO. And those are both examples of bottom-up procedures. So you use the bottom-up procedure when you assume that your chemical is a non-irritant. If you assume that your chemical is irritating, then you use the top-down approach, which means that you should start with the BCOP LLBO. First, a little bit of background on the selection of the physical chemical properties. This was based on a bigger data set, where we looked first with principal components on which properties that could explain classification. And next, classification trees were used to determine the cutoff values. And you can see if you would use log P on its own, then you would underpredict 50% of the cut ones and the cut twos. So this is definitely not a good choice. This is the same for the other, for the vapor pressure and the surface tension. You cannot use them on its own. But if you combine the three properties, then you can see that none of the cut ones or the cut twos are false negatives. And for the water solubility, there was only one liquid that was a false negative. What is the reasoning now behind using those physical chemical properties? Well, this is because some of the in vivo no-cut liquids that are false positive based on the RH-CE test method. So they are irritating according to the RH-CE. Well, if you use the physical chemical properties exclusion rules, then they are correctly identified as no cut. And in fact, by combining the physical chemical property exclusion rules with the RH-CE test methods, the specificity of the defined approach increased with about 10%. So that's the reason why the physical properties were used. Which methods can you use to look at the physical properties? well, you can measure them according to the different guidelines that are mentioned here, but be careful for the surface tension. It's not exactly according to guideline 115, because there the surface tension is measured of an 1 gram per liter solution, and we use the surface tension of the neat liquid. You can also use QSOR tools, and for the log P vapor pressure and water solubility, we used Opera. There is no Opera model available for surface tension. For this one, we use Test. All of them are open source tool-based methods that were developed according to the five OECD principles for QSOR models. So it means that they have a QMRF or a QSOR model reporting format. And then here you can see the sources where you can obtain such a kind of data. Then we'll look at the performance of the defined approach 1. So during the development of the defined approach, and after submitting the defined approach to the OECD expert group, performance criteria were agreed by the OECD experts. And those performance criteria, they take into account the uncertainty of the Draize eye data that was clearly explained by Joel. So in green, you see the minimum correct prediction rates. In blue, we have the under predictions that are allowed, and in yellow, the over predictions or the false positives. Then DL1 was evaluated based on 94 liquids in total. So 17 cut 1s, 22 category 2s, and 55 no cut liquids. And 67 of the cut 1s were correctly identified, 59 of the cut 2s were correctly identified, and 70.5 of the no cuts were correctly identified, resulting in a balanced accuracy of 68.7. And the balanced accuracy is the average of the values in the green cells. The DAL1 with VRM2, so with the schematic, was based on an evaluation of 86 reference liquids. There is overlap between the set of 94 and 86, but especially for category 1 and category 2. But for the no cuts, there is less overlap between the liquids that were evaluated. Then for the cut 1, the correct prediction rate was 76.5. The same as DAL1 with VRM1. Here the prediction is based on the BCOP opacity. BCOP opacity. For the category 2, we have almost 68% correct. And for the no cut, we have almost 80% correct, resulting in a balanced accuracy of 75%. Then I will illustrate the use of the DL1 with isobutanol, which is an in vivo cut 2 liquid. So if we look at the chemical properties and the values of the properties are in the column in the middle, and they are based on the QSOR models, you can see that none of the exclusion rules were met. So it means that we have to continue. And then the next step is look at the cell viability with VRM1 or VRM2. And the cell viability in both methods was very low. So it means that the compound was irritating. And then the next step is to look at the BCOP LLBO. And the opacity was 104, which is below 145. So the final prediction is category 2. At the right-hand side, you have the same methods, the same values, but here we start with the top-down approach. So it's just to show you that, yeah, the order of the different methods, of the different components in your defined approach can be determined by yourself. So, and we come to the same conclusion that isobutanol is predicted category 2. So independent of the that you use the top-down or the bottom-up approach, you come to the same conclusion. Then I have a second example with an butyl acetate, where we start with the RH-CE. And the viability is again below 60%. So it means that according to the RH-CE, the liquid is irritating. And this is here an example where we have to do with a false positive based on the RH-CE. But if you look at the combination of the log P, vapor pressure, and surface tension, then you can see that the exclusion criteria are met. So based on the physicochemical exclusion rules, the prediction will be a no cut. Then the components of the second defined approach, DL2. There we use OECD TG491 to identify no cut and also category 1. So it's the short time exposure test method, where the eye hazard potential of a chemical is based on its ability to induce cytotoxicity in Circ cells. Those are rabbit corneal cell lines. And the second method is the OECD TG437 to identify category 1. And again, the VCOP LLBO method is used, and we use only the opacity. Here you can see the scheme for the bottom-up approach. So in the Sde test method, the test chemical is tested, applied to the cells at a 5% concentration and at a 0.05% concentration. And if the cell viability of the cells is above 70%, then the chemical is predicted no cut. If the cell viability at both concentrations is below 70%, then the chemical is predicted category 1. In all other cases, then you have to continue with the BCOP LLBO to come to your final prediction. And again, the opacity with a cutoff of 145 is then used to distinguish category 2 from category 1. We can also switch the methods, and then you have a top-down approach where you assume that your test chemical is irritating, and you start with the method to identify the category 1. The cutoffs and the rest of the scheme is exactly the same. Then, yeah, the same performance criteria were used, of course. And the performance of DL2 is based on a set of 164 liquids. The CAT1 and CAT2 liquids were basically the same for DL1 and DL2. With the only difference that here also dilutions are included of liquids or solids. And then the no-cut set of chemicals was 123. You can see that more than 80% of the CAT1s were correctly predicted, 56 of the CAT2s were correctly predicted, and 85 of the no-cuts were correctly predicted, resulting in a balanced accuracy of 74%. And then here is an illustration with the case studies on 2 chemicals. And the chemical on the left is an in vivo category 1 chemical. And you can start, for example, first with the Sce Test Method. You can see that the viability at 5% is 6.4, which is far below the 70% cutoff. But at 0.05, the viability is high, so above the 70%. So it means that we need a second test, the BCOP LLBO, to distinguish between category 1 and category 2. And the opacity measured in the LLBO was 172, which means that the chemical is predicted category 1. The second example on the right side is with glycerol, which is an in vivo no-cut. And there we start with the Sde Test Method. You can see that the viability at both concentrations is above 70%. So it means that the chemical is predicted no-cut. So I did not show all the possible variations of the dip, but for all the defined approaches, we had all the data. So it means the Viscamp properties, the STE data, the BCOP data, and the RHCE data. And all the different combinations of the DAs resulted in the same prediction. And furthermore, the prediction was the same as the in vivo method. So here we can show that with those case studies that the DAs are applicable to distinguish between the 3 UMJHS categories for eye hazard identification. And then, so I come to the conclusions. We have illustrated the applicability, the use of DL1 and DL2 with 4 chemicals. We also showed different variations of the dip that resulted in the same prediction. Also, the bottom, whether you start with the bottom up or the top down, the result was the same. So we came to the same prediction. So with the case studies, we can show that how we can move from animal testing to defined approaches for safety purposes of ingredients. And both defined approaches are part of the new OECD TG 467. And so they can be used in a regulatory framework for eye hazard assessment of non-surfactant liquids. And that was the last slide of my presentation. So thank you all for listening to me. And I will now check if I can answer some of your answers. Thank you, Eugene.
Thank you very much, Els. While Els stop sharing the screen and our next speaker, Natalie, starts sharing her screen, I just like to perhaps give a bit of background about the defined approach for those who are not familiar. So like the IATA, the integrated approach to testing and assessment, the defined approach has a DIP that is a fixed without being subjected to experts' opinion. So as a whole, it's accepted as a OECD test guideline. So this is the first, Natalie, are you starting to share your screen?
Yeah.
Yeah, you can go ahead, yes. So this is the first defined approach for eye irritation endpoint, and it demonstrates importance of a holistic approach to overcome weakness and the limitation of individual information sources mentioned, now arriving at a standalone test method that can fully replace the in vivo Draize test. And now here is another example of such a test method, which will be introduced to you by Natalie Alette from Lorraine. Okay, thank you. Natalie, floor is yours.
Eugene, you could see my screen?
Yes, we can see.
Yeah. Okay. So good afternoon, everybody, or good morning. We are from US. So then I will present now the kinetic HE time to toxicity, which is the first model that have been adopted in the test guidelines 492B for the eye hazard identification. Then just to build on the Joao presentation, just to highlight that it's also related to the full replacements of NAM and namely the 492B. So this one, I think, slide again, it's one of common slide we share with Dr. Adrians to just let you know that the main issue up to 2021 was that no single in vitro method was fully adopted to replace the in vivo Draize test for eye safety evaluation, and health just presented before to you that now there are some opportunity, or at least a combination of in vitro NAMs to do that for liquids, either neat or in dilution. The proposal and what I will talk today and more focusing is that of a new method that has been submitted to OECD last year and gained regulatory acceptance as a standalone test methods for discriminating on its own the 3 UN JHS category, namely category 1, 2, and no CAT, as has been described by Dr. Barroso just before. So briefly related to these methods, in fact, the test system consists on the skinetic human corneal epithelial, so namely the HEE, which in fact consists of a human corneal epithelial constructed with human immortalized corneal epithelial cells. And indeed, it's a multi-layer epithelium that resembles to the in vivo epithelium with similar thickness, morphology, and histology. What we did was based on our knowledge, I would say, in terms of the expertise of these kinetic HE models, meaning the test systems that were used also for the OECD TG492 that has presented just before in the combination of the PCOP, but also our knowledge of developing methods. In fact, we associate both new protocols with this test system, and we come up with this protocol for which indeed 2 protocols distinct for liquids and solids were needed. And typically it's some HE tissue that are topically exposed to substances. So either the control of the test substance, and the test substance could be either solids or liquids neat or in dilution or mixtures. And for the liquids, you have 3 exposure time, either the 5 minutes neat, 16 minutes, 20% diluted, or and 2 hours, 20 minutes diluted. For the solids, the protocol consists of 2 exposure time, with the solid as a neat solid to be applied onto the HEE for 30 or 120 minutes. Then the protocol is quite very standard, where you measure the tissue viability by enzymatic conversion of the vital dyes entity into the blue entity from azote salt. And indeed, you quantify this by extraction from the tissue. And then you determine the cell viability in reference to the negative control substance, which is considered as 100% of viability. And from that, you could then define prediction models. And so based on the viability observed from the different exposure periods, so the 3 from the liquids and 2 for the solids, we could define a classification, and this classification was assigned as described in this table. So for example, for the liquids, if all the cell viability at any time of exposure, 5, 16, and 120 minutes were above 50%, then the chemicals were classified as no categories. Whereas for the category 1, to be classified as a category 1, the cell viability was below or equal 50% with all those terms. Any other combination of value led to a classification as a category 2. Similar approach was done with the solids, knowing that the cutoff was for the short exposure time, 40%, and 60% for the 120 minutes, so the long. So what we did, in fact, to go through the development of the methods, and I would say to minimize the uncertainty associated with the in vivo reference data, we selected the chemicals from the Draize eye irritation test reference database, as Joel Garrison just explained you before. And so we also follow the recommendation of this for the selection of the chemicals for the validation study. So all the chemicals that were selected here, over the 151 chemicals, met those selection, except one, to be fully transparent with you, to really minimize such a high uncertainty. The majority of these chemicals indeed represent monoconsistent substances tested net, but some were also in dilution, and the dilution ranged to 0.01 to 30%. So we cover both, I would say, monosubstance, nets, or in dilution and few mixture also. What was important also in terms of the selection and so on of this NAM was that we represent different generic classes. I mean, soaps, surfactants, neutral, anionic, organic, inorganic, salt or acid, base, and so on, to cover the main, I would say, generic class. But was also important when we come up to the selection was to cover also the different functional class, such as, for example, ester, amide, alcohol, alkane, amine, and so on. So I will not go through all this list, but most of them were there. And also what we did is to complete this chemical distribution space, we looked at the physical chemical properties, like a very standard one, like a molecular weight, melting point, water solubility, log P, vapor pressure, and surface tension. And you could see that here is the distribution of the chemicals that were evaluated. So 70 liquids and 81 solids that were quite well balanced in terms of the distribution through the category 1, category 2, no category, and liquids versus solids. So we did not develop the methods with those 151 chemicals, but with almost 74 chemicals that I named the training chemicals, which consist of 32 liquids and 42 solids, and therefore these were challenging. And those chemicals were mainly selected based on the important in vivo driver of classification, such as corneal, conjunctival, and persistent effect, as it has been presented by Joel Garrison just before. Once we did that, what was important for us was to look at the reproducibility of these methods. And so what we did was to perform an internal reproducibility of evaluation of all the chemicals that were tested within L'Oréal. And we did that in 109 chemicals that combined indeed training and test sets. And the reproducibility was above 87%. And here you could see what the green bar represent the concordance between the run we obtained, and the blue one represent the where we did not get concordance. And you could notice that there is no specific category of chemicals or per driver of classification that show really such a no concordance. What was important then was to conduct a blind multicentric study. And this has been conducted with 40 chemicals in 3 other labs to demonstrate the reliability of both the time to toxicity protocols, both on liquids and on solids. And indeed, the within laboratory and between laboratory reproducibility was assessed on 40 chemicals that were double coded in 3 laboratories, namely Episkin, Eurocef, and Vitroscreen. And here you could see on the left side the reproducibility of the 20 liquids that were tested. So the dot plot represents by color the 9 runs that were conducted, so 3 per laboratory. And you could see, for example, for this orange chemicals, that there is 8 classification or 8 runs that classified these chemicals as category 1 and 1 that were not reproducible. And we did it for the liquids and also for the solids. And indeed, for the solids, all the chemicals were highly reproducible, and we get 100% reproducibility for the 3 labs. For the liquids, you could notice that for few chemicals like this orange or this violet here, we get some discordance between the labs. Overall, by considering liquids and solids, you could see the different performance of the 3 independent labs, where at least 37 out of the 40 chemicals that were tested show within laboratory reproducibility. Considering the between reproducibility, the between lab reproducibility reached 95%. What was also important to go through when we developed this method was to evaluate the predictive capacity. And this predictive capacity was calculated based on the individual classification using the prediction models that I described previously. And also, what was also important was to check this predictive capacity compared to the minimal performance metrics for the 3 UNGHS category proposed by the OECD experts. And you could see here that the OECD performance metrics that were agreed within the expert group was that at least 75% of the category 1 chemical should be identified as a category 1, 50% of category 2, and over 70% of no-cuts. Here you could see in this graph the representation per category and then by the driver of classification and either liquids and solids, how each category of chemicals per driver perform. And you could see that briefly in green, it's what was considered as a true negative or true positive chemical, so correctly classified as expected. In blue, it's what has been considered as a false positive, meaning that those chemicals were over classified. So for example, you could see for the no-cuts that there are few chemicals that were over classified as category 2 or even category 1. And for the orange, those chemicals were under predicted as a Cat 2. And so in red, that there are some false negative for which those chemicals as a category 2 were under predicted as a no-cut. Overall, considering those 151 chemicals that were evaluated, we reached an evaluation or a prediction of the category 2 of 79%, 69% of the category 2, and 75% for the no cats, with an accuracy of 74%. Just to illustrate with few examples, or at least 3 chemicals, what we did, and here I illustrate with liquids just to fit with what has been just presented by Health Adrians before. I consider here 3 case studies, 3 chemicals. So the chemicals 1,3-diisopropylbenzene, the 2-methyl-1-pentanol, and the 2-hydroxy-isobutyric acid ethyl ester, which are liquids, but I can show similar case study with the solids. And here, knowing that those are liquids, so we fit with the prediction models, where everything above 50% at all time treatment will be classified as no category, and below or equal 50% will be classified as category 1, and then any other combination of that. And you can see for the 3 examples that I took that, for example, for the first chemicals, at the 3 exposure time, the cell viability was strictly above 50%, leading to a classification as no cats. For the category 1, that everything, the cell viability was below 50% as all time treatment, leading to the classification as a cat 1 of the 2-hydroxy-isobutyric acid. And as an illustration here for the category 2, you could see that it was either below or equal to 50, and then above 50 when you consider the application of this chemical 16 minutes diluted on the tissue. Here I took an example where the in vivo classification of the test methods correlate to the in vivo data. So just as in conclusion, Infighted, the first method, considered as a standalone method that has been adopted for regulatory acceptance for and to distinguish on its own the high hazard identification. The reproducibility and the performance have been demonstrated to distinguish between those 3 UNGHS categories, and this for liquids and solids. No functional group has been identified to be out of the applicability domain so far. And we'll say that's really, as we pointed out before, a gap in terms of regulatory and for safety assessments of the ingredient has been filled with this approach. And to my point of view, it's really a major step in the battle towards the end of the animal testing. So thank you so much for your attention.
Thank you for the presentation. We are unfortunately over the end of the time for the webinar, and I would like to thank the speakers who've already addressed some of the questions that were answered to the Q&A chat. I took a look at it briefly, and it seems many questions are around the specific applicability domain for the defined approach and the TG492B. And I would like to direct you to the actual guideline and all the necessary technical documents, including the SOP, are referenced there, and they do have a detail on how these test methods can be used. So I'd like to welcome you visiting OECD Test Guideline website and look at those documents for the specific of the applicability domain and so on. For now, I don't, as we are already late with time, we will not be able to further discuss other comments, but as I said, mostly they were technical and the answers can be found on our OECD Test Guidelines. With that, I would like to again thank all the participants who connected from all around the world to learn about this remarkable achievement in the community, developing the first standalone test methods and also the community's efforts in really trying to pin down into the accuracy and the reproducibility of the database that can be used for the future test methods they will come. And I again would like to thank the speakers for their time and the presentation. And with that, I would like to conclude the webinar. As I mentioned in the beginning, all the presentations as well as a recording of this webinar will be available later on our webinar website. So yes, hopefully, and we will see you again in the future with different webinars to connect with you in other contexts as well. Okay, thank you very much. And I wish you have a good day, good afternoon, good evening. Thank you. Bye-bye.